So we've built a binary counter, and we're going to use this to actually count how many times you push a button. I know, you're wondering, what on earth are you doing to us, Juby? Okay, just work with me here, okay? I'm trying to show you something, okay? We're going to essentially use the same circuit from the last lesson. However, we're now going to switch to from an external clock signal to the internal clock running at 16 megahertz. We're going to put a push button wired onto input RA0, which is our digital input-output on port A. This is pin 13 on the chip itself. We'll set up the program so that every time we push the button, our binary counter counts up 1. Seems pretty simple, eh? There's a sneaky little problem here I want you to see firsthand so you can be as amazed as I am every time I deal with this. Okay, so once again, the code is available to just copy and paste. You can copy and paste it into the assembler window of the binary counter project if you want. Or again, you can practice building a new project from scratch. See if you forget something in the setup and crash it all when you go to try and program it. You can leave the 555 on the board if you want. We're setting up the chip to ignore that input anyway, but we won't be using the 555 on any more of our PIC projects. So if you want to keep it there for your own personal use as you experiment with the PIC, go for it. Or you can remove it from the board completely. So let's take a quick look at the code where you'll be introduced to a couple of more instructions. Now, in the fuses section, we've really only made one change, and that's here. The FOSC register, which is the register that sets the frequency of the oscillator, the clock. We've changed it from an externally determined clock to the INT-OSC, or internal oscillator. So the clock inside the chip. It defaults to 16 megahertz, though you can change that frequency in a couple of different ways. We'll get into that in a later lesson devoted to these fuse settings. The first line sets the bank that the tri-state C register is in. On the PICs, there are usually multiple ports. On this PIC, we have a port A and a port C. And you remember many of these pins had multiple functions. They have 3 different states, basically. They can be a digital input, reading a high or low signal coming in. They could be used as a digital output, sending out a high or a low. Or some pins could be set up as an analog input to read a varying voltage on the pin. So there are these specific tri-state registers for each port, and you set up the port to do what you want. Now, port C only has 6 pins, RC0 through RC5. So the TRIZ-C register has a bit associated with each port C register. The top 2 bits don't matter because they're not connected to anything anyway. So if I send a binary number of 001-01101 to the tri-state C register, then everywhere I set it to 1 becomes a digital input, and everywhere it was set to 0 becomes a digital output. So in this example, RC0, 2, 3, and 5 were all set to inputs, and RC1 and 4 were set up as outputs. I'll get into the analog settings in a later lesson when we actually use the analog inputs. So in our program, I first selected the correct bank. Very important. I cheated and told it to set the bank to whatever bank the Tri-C register was in, and then I cleared it. I set all the pins to outputs. I then switched banks to the one that holds the TRIZ-A register. Interestingly, I didn't really need to do that here because it so happens that the TRIZ-C and TRIZ-A are in the same bank on this PIC. However, you remember we used that include file right at the beginning for ease of use, so ease of programming, but also so we could transfer this program to another different PIC processor. So I'm just thinking ahead here. It's a single line of code, not a lot of work to type in, but if I now transfer this code to another PIC micro, and the TRIZ-A register happens to be in a different bank than the TRIZ-C register, I got my bases covered. We then put in hex FF into the working register, all 8 bits high. We then move the contents of the working register to TRIZ-A. All pins connected to port A are now set up as inputs. Now we're only using one of these inputs, so it's overkill, but hey, it was simple. We set the bank to the latch C register, which is the register we actually write to write to port C, and its bits also correspond to the port C bits. Now we can write directly to port C if we want, instead of writing to the latch, but I'll explain why later on. It's technical. We clear the latch, so now all of our outputs on port C are low. We make our first label, loopy, loopy 1, and we then select the bank for port A. We need to do this because port A is in a completely different bank than the tri-state registers or the latch registers. We then come to that bit test check again. Only this time we're checking the input on bit 0 of port A, the pin our button is connected to. If we push the button, we'll read a high on that pin. So the specific command is to test bit 0 on port A if it is cleared. That's the C for clear. That means the button is not pressed. We're going to skip over the next command. So we haven't pressed the button. It skips over and gets to the command to go to loopy 1. It then loops back over and over again, 16 million times per second, until you finally press the button. When you do, the bit test shows the bit is set, held high. So it does not skip the next command. The next command calls a subroutine. There's our first command to call the subroutine. Now, labels like loopy 1 or button press can be used as landing points for commands like go to or call. Now, if I tell it to go to, it'll just go to the label. But if I call a label, what will happen is that it will go to that label, it will run the code there until it sees the command to return. There's the command down there at the end of the button press subroutine. Now, you remember Dan the man with the stack? Here's where he comes in. So he remembers where you left off, right here, and stores that line in his stack. So when you issue the return command, he'll bring you right back to here, right where you left off. Go to doesn't do that. Go to goes there with no expectation of returning. Dan the man doesn't remember from whence you came and doesn't care. You're just, jumping around the program with the go to command. So we call the subroutine, jumping down to button press. The first thing that happens there is we select the bank for LATC because we need to work on that register. We then do exactly like we did in our original binary counter. We check to see if it's gotten to 16 in the count yet or not. If it has, then it sets it to 0 and starts the count over again. It then carries on down the line of code. We select the bank for port A and check to see that port A is reading a low on bit 0 because we have released the button. If we are still holding that button down, then it will jump to the label button up, which is up here. And it will keep doing that until we release the button. But bit 0 on port A shows a low, and the bit test tells it to skip the next command. And it jumps to the command return. It now goes back to here and continues this loop over and over again, awaiting your pressing the button again. Okay, I hope that makes sense. Now, the schematic is in the download section, and once you have it built, you've flashed the program onto the PIC. Try it out. it'll count up every time you push the button. But it's going to malfunction. I want you to play with it for a while and see if you can figure out what's going on. Now, if you're really smart, you might even figure out why it's doing what it's doing. Now, then in the next lesson, we'll talk about what's going on and what to do about it.